One interesting tool in mathematics is what we call the Pascal Triangle, which is named after Blaise Pascal. It is a triangular arrangement of numbers. Pascal triangle is symmetrical about the vertical axis. It has ones on its left and right edges. There are a number of patterns that we can discover using this Pascal triangle. One is finding or discovering that any number could be a sum of two numbers on top of it. Let's say, for example, I choose 21. It's a sum of 6 and 15. 120 is a sum of 84 and 36. Now, you can just find any number here and express it as a sum of two numbers on top of it. We also have counting numbers, and they appear after the edge that contains ones. Natural numbers are simply counting numbers, so you count starting from 1, then 2 and 3, and so on. Triangular numbers are numbers that can form equilateral triangles. So we just form these equilateral triangle from several numbers of dots. I say, for example, for 3 dots, you have the first equilateral triangle, and then 6 dots, 10 dots, and so on. Although this pattern starts with 1 dot. Another pattern that we can see here is that the horizontal sum is a power of 2. So we have horizontal sums 1, 2, 4, 8, 16, 32, 64, and so on. And these are powers of 2. 2 to the 0, 2 to the first power, 2 to the second power, 2 to the third power, and so on. If you take the sum of half diagonals, you will have numbers like 1, 1, 2, 3, 5, 8, and so on. And this is a Fibonacci sequence. If you remember, Fibonacci sequence is a number that is a sum of two numbers preceding it. So let's say 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 is 13, 8 plus 13 and 21, and the pattern continues. The numbers along the horizontal form powers of 11. So we have 1, 11, 121, 1331. However, from 11 to the fifth power and so on, you may need to overlap some digits to form numbers which are powers of 10, as shown in the diagram. The Pascal triangle is very helpful in binomial expansion in the form quantity x plus y raised to n. Let's say we are expanding it to the second power, so our expansion will be x squared plus 2xy plus y squared, which is written in red mark and with coefficients 1, 2, 1 respectively, which can be found in row 2, the numbers in row 2, 1, 2, 1. Okay, let's expand x plus y to the third power. The answer is x cubed plus 3x squared y plus 3xy squared plus y cubed, and it has the coefficients of the terms 1, 3, 3, 1 respectively, which can be found in the numbers in row 3, 1, 3, 3, 1. These coefficients can also be obtained using combination n takes r. Let's say we are expanding the binomial to the fifth power. Then we shall have 6 terms. If I expand the binomial to the fourth power, I will have 5 terms. Let's expand it to the fourth power. The expansion is written in green color. Let's study the coefficient. If we're going to use the Pascal triangle, we can find it in row 4 with numbers 1, 4, 6, 4, 1. But if we're going to use combination, n takes r, then we shall have for the first term 4 takes 0, which is 1. For the second term, 4 takes 1, 4. And for the third term, 4 takes 2, 6. For the fourth term, 4 takes 3 equals 4. And then for the last term, 4 takes 4 is 1. And you can see that it's similar to our numbers in row 4. If I color all odd numbers with just one color, in this case I use blue, and all even numbers as one color also, in this case I use white, I form Sierpinski triangle. Sierpinski triangle is an example of fractals, and fractals are never-ending patterns, and they show self-similarity across scales. You can use this triangle to discover some more patterns.